So continue on with some hints, broad hints on what to do when you get stuck, how to go about proving stuff. So the last one we mentioned, come back to it. So we talked about this one. Let your unconscious do some work. So don't give up just after one try. Keep at it, because you may have a new approach on later attempts. So two more. Be neat. Be clear. Like if you have a notebook, try to make it neat, because if it's just a mess, you're just writing down little squiggles and you're making a calculation. It may be meaningless to you when you come back to it and you look at it. What you may ask, what was I doing there? Like a similar comment, if you're a programmer, it's advisable to put lots of comments about your code, because you probably know if you've ever programmed a computer, if you come back to your own code 6 months later, you say, what the hell was I doing there? So if you don't have lots of comments to help yourself, or certainly somebody else trying to read your code and understand your code, it can be extremely difficult. In fact, a lot of people take the view that it's easier just to recode yourself than try to understand someone else's code. Debatable. Anyway, but similar thing with trying to prove theorem statements is be neat in your notes, so that you and maybe other people can follow what you've done. So and be clear, right? So that you can go over your own stuff and know what you were talking about. It's just easier to follow than just some chaotic mess, right? And be concise. Be as concise as you can be. There's a limit, of course. You can if you don't have enough details to be clear, then it's counterproductive. So to the extent that it's useful to be concise, be concise. So you go to the heart, what you consider to be the heart of your potential proof, the essential idea or ideas. Like for example, earlier, the main idea. Each time you add one more edge, that increments the total of the degrees of all the nodes in the graph by 2. Once you had that essential idea, and the proof pretty well, that was the heart of the proof. So once you feel in a proof that you've got the essential idea, write it down concisely. And now, if it's detailed and there are lots of steps and whatever, you'll need enough details to be clear, because clarity. Be neat and be clear. Right? So clarity is important. Okay, now next thing. So this is theorem 0.20. These reference numbers are taken directly from the text, so you know where we are in the textbook. So what we're going to do now is we're going to do our first actual proof, a pure math proof, to give you a feel for, to make more concrete, the sort of the vaguer, woolly hints and rules of thumb I've done so far. But this is our first real proof. Okay, as it'll be an example of what a proof is like. So here's typically a proof. Now there are no lemmas in this case, because it's fairly simple, right? There are no parts in a sense. Well, actually, strictly speaking, there are 2 parts, but no lemmas for this case. So theorem number, that's fairly typical. The statement of the theorem statement, and let's actually do it. So this theorem statement involves two sets, right? And the theorem says that this particular set, whatever it is actually equal to this particular set. And they look quite different, right? The left-hand side just looks quite different from the right-hand side. But you're asked to prove that this set and this set are the same. In other words, they have the same members. Okay? So that's the theorem statement. In fact, this theorem, or theorem statement, is actually one of De Morgan's famous laws involving two sets. If you don't know what this is, don't worry about it too much. Just concentrate on this set, and you have to prove that they're equal. Right? That for any two sets A and B, this equals this. Right? That's the statement. Now we have to go about proving it. So typically, after the theorem statement, you'll write the word proof. It's pretty standard in pure mathematics, certainly in this text as well. Let me just check. Let me get a proof rather than a corollary statement. There should be lots of them. All right. Well, I'll get. This particular author. Okay, here's one. Tends to it's not so stupid actually. Sipser. When a proof is quite difficult, he tends to, after the proof statement, he will have I think was it like outline of proof? A proof idea. So he will give a few paragraphs about the general idea of the proof, the motivation behind the proof, the essential ideas in the proof, and then the proof itself, in detail. And that's not a bad idea. But usually, well, especially if the proof is not too hard or too long, you don't bother with like proof idea. That's more for it's a textbook, right? So it's more for didactic purposes, to aid teaching. That's the meaning of the word didactic. All right, so I'll show you. This is on page 245 of your text. Now I'm talking about the second edition. Here's the text. If you're getting it in English, it'd probably be this. So, Introduction to the Theory of Computation, second edition, by Sipser, Michael Sipser. And I have the Chinese edition, so I don't even know what this says. I assume it's Theory of Computation. God, I'm so frustrated by the Chinese writing system. An incredibly stupid, primitive writing system that should have died centuries ago, but it's just been kept up by tradition. And so 1 billion or more people have to go through the torture of learning thousands of characters instead of an alphabet with 24 characters or 24 symbols. I mean, it's just so incredibly stupid. I just get annoyed every time I see it. Okay. Alright, so on page 244, if you can, I don't know if you can see that, I'll get fairly close. So here's your theorem ID. So theorem 6.31, so we're in chapter 6, it's theorem 6.31. Here is the theorem statement, and then usually the word proof, and then the proof starts. Okay, the actual logical argument proving this statement. Right? Now does he? Now this guy's not a mathematician, right? So he doesn't seem to have the same conventions that pure mathematicians use. I'm just wondering, like, how do you know? Yeah, get back in. How do you know when the theorem proof is finished? Now in this case, he just says, and the theorem is proved. So he just uses words. So let me have a look at some of the other proofs. How do you know when a proof is finished? because that's useful to know. And the proof is complete. So is that how he does it? And the theorem is proved. Well, then it's just got a line at the end. Proof. And he's got a line. Okay, so either he's using words or a line or something. Now, in pure math, nowadays, it's pretty much a strong convention now. It took a while to establish, but yeah. Now I'm jumping ahead a little. You see this vertical rectangle that's hollow, so just 4 lines like this. This symbol here is, amongst the pure mathematicians, mathematical physicists as well, increasingly, influenced by the mathematicians. This vertical hollow rectangle is the end of proof marker. It's a sign that tells you that it's the end of the proof. Right? Now, earlier often you'd see QED, which serves the same function. It's an end of proof marker, or a sign that it's the end of the proof. And QED is short for, it's Latin, quod erat demonstratum. In other words, as was to be proved. Right? Now, quite a few authors, a bit earlier, now I think virtually everyone, pure math at least, has latched onto this end of proof marker. But before, like earlier decades, you'd see this kind of thing, like again a vertical rectangle, but filled in. But I guess for the printers, this is just easier to do. Okay, so you don't need to write words, as was to be proved, or the proof is now complete, or a whole line, which will just waste a line. Right? You just put a little marker like this. So I suggest, strongly suggest, that when you finish your proof, you put this little mark, so that your reader knows that you have finished, or the reader has finished the proof, or your proof in a book or article or whatever has finished. Okay, so that's useful. So you start the proof with just literally the word proof, right? And then all your proof, and you finish, and here's your end of proof marker. So start sign, end sign of your proof. All right. Well, let's actually do it. So this is our first proof, full proper proof in the whole course. So a little bit of history being made. Ta-da! So the proof statement says these two sets are equal, and we have to prove that. And you remember from earlier discussion, how do you go about proving that two sets are equal? Well, by showing that one of them, let's say the left-hand side, is a subset of the right-hand side, and, don't forget and, the set on the right-hand side is a subset of the set on the left-hand side. So in other words, you have to prove that two sets are equal,